Hey guys, welcome to lesson 2. So today we're talking about special right triangles. Someone recommended to me that I need a catchphrase. So when we start the videos, as soon as I say let's get cooking, that means we're going to start getting into the math. So let's get cooking. Let's talk about special right triangles. So first thing we're going to do is we're going to take this triangle and solve for x in the right triangle below. The reason we're doing this is next lesson we're going to create something called the unit circle. And the unit circle is a radius with a length of 1 unit. So this is 1 unit right here. So what we're going to do is we're going to take the fact that this hypotenuse is 1 and try to find each of these legs right here. So when I look at this, a couple things I notice. First thing I notice is the legs are the same length. So if the legs are the same length, this triangle must be an isosceles triangle, specifically an isosceles right triangle. And remember back to your geometry days, isosceles triangles have 2 sides are the same, which means that the base angles right here are also the same, which means that these 2 angles right here must both be 45 degrees. The reason they're 45 degrees is we know that all the angles in a triangle add up to 180. This angle is already 90 degrees, so these 2 must add up to 90, and they have to be the same, so they're both 45 degrees. So now we're going to use Pythagorean theorem to help find x, and I found those 2 angles because we're going to name these special right triangles by their angle measures. So we're going to use the Pythagorean theorem now to solve for x. So I've got x squared plus x squared equals 1 squared. So I've got 2x squared equals 1. X squared equals 1/2. Then I square root both sides. So x is going to be equal to the square root of 1/2. Technically, this should be x equals plus or minus square root of 1/2, but because these are side lengths, we know that they're not negative, so we're only going to use the positive square root. So remember, with fractions, I can square root the numerator and denominator separately. So this is 1 over the square root of 2. But we don't like radicals in the denominator of fractions, so we're going to rationalize by multiplying by the square root of 2 over the square root of 2. And remember, the reason that this works is square root of 2 times square root of 2. I can multiply those 2 together because they're underneath the radical. So that is square root of 4. So I've got square root of 4 down here, and the square root of 4 is 2. 1 times square root of 2 is square root of 2. So x must be equal to square root of 2 over 2. So I've got square root of 2 over 2. So with this first special right triangle, there's a relationship that exists where if I take a leg and multiply by the square root of 2, it'll give me the length of the hypotenuse. So if I try that here, if I take square root of 2 over 2 times the square root of 2, that is square root of 4, which the square root of 4 is 2. 2 divided by 2 is 1, gives me the hypotenuse right here. Alternatively, if I take the length of the hypotenuse and I divide by the square root of 2, it'll give me the length of the leg. So 1 over the square root of 2, which we actually did right here, and then rationalize it, gives me a square root of 2 over 2. There's going to be a page coming up that has these rules on it, so don't worry about writing them down right now, but I'm just showing you the way that that relationship works in special right triangles. And specifically, this kind of special right triangle we're going to refer to as 45, 45, 90. Or an isosceles right triangle. So that is our first type of special right triangle. The second one is going to come from an equilateral triangle. So we're going to show how this works using an equilateral triangle. So what we have here is ABC, an equilateral triangle where all the sides are length 1. Again, remember, the purpose of this is going to be the unit circle coming up next lesson. So we're going to look at this hypotenuse, and we're going to assume this is a right triangle. We're going to explain why in a second. We're going to look at this hypotenuse and say this is 1. All right, so what we're going to do here is this is an equilateral triangle. And right here, I've drawn in an altitude. So an altitude of an equilateral triangle does a few things if you remember from geometry. One is it bisects this angle. So if I'm trying to find the measure of angle DBC, this angle ABC was 60 degrees because it's equilateral. So all the angles are the same, they're up to 180. So each angle is 60. So then I look at DBC right here, and that must be 30 degrees Because in an equilateral triangle, the altitude bisects this angle right here. Another thing that it does, the altitude bisects this segment. So this is 30 degrees, and it bisects this segment AC, which means AD must be equal to DC. If AC, the whole length is 1, then DC must have a length of 1/2. So the length of DC must be 1/2. Now it's asking us to find the length of BD right here. And really, we can't do this, and well, we could once we know the law of sines and cosines, but right now we can't do this without knowing whether or not this is a right triangle. So properties of that altitude come in handy once again. So this altitude right here also is perpendicular to the opposite side, which means that this is a right angle, meaning we now have a right triangle we can use to help us find BD. And I don't want to call it X, so I'm going to call it M. We're going to solve for M. So again, we can use the Pythagorean theorem. We've got 1/2 squared plus M squared equals 1 squared. All right, so we've got 1/4 plus M squared equals 1. M squared equals 3/4. So then M is going to be equal to the square root of 3/4, which we know we can square root the numerator and denominator separately. So this is the square root of 3/2. Again, technically this is plus or minus square root. But in this case, as we're talking about lengths of sides, we're going to use the positive square root. So this is square root of 3/2, positive square root of 3/2, not negative. All right. So this is another kind of special right triangle. This is the 30, 60, 90 right triangle. So we already explained why this is 30. We explained why this is 90. Then this must be 60 because, well, first of all, it's an equilateral triangle, so that angle must be 60. But in case you couldn't figure that out, if this is 90, this is 30. 90 plus 30 is 120. All the angles in a triangle add up to 180, which means 180 minus 120 gives us 60 degrees here. All right. So here, there's a relationship that exists where everything is going to circle around the short leg. And I'm actually going to show you this rule on the next page because this page is getting a little bit cluttered. So the rule for 30, 60, 90 triangles is to focus on the short leg first. So you can identify the short leg because it is across from the 30-degree angle. Makes sense, 30 degrees is the smallest angle. It should open up to the smallest side on the triangle. So we start with a short leg. And to go from short leg to hypotenuse, you multiply by 2. To go from short leg to long leg, you multiply by the square root of 3. And we can actually go back and verify this in our previous example. This was 1/2. So to go from the leg to hypotenuse, multiply by 2. 1/2 times 2 is 1. To go from the short leg to the long leg, you multiply by square root of 3, which is square root of 3/2. If you want to go the other direction, so like let's say you wanted to go from long leg to short leg, instead of multiplying by square root of 3, you would divide by the square root of 3. And then same thing with hypotenuse. Hypotenuse to short leg, you would divide by 2. All right. And then over here, like I said, there was going to be a page with a rule for the 45, 45, 90 triangle. If you're taking notes, which you should be, I would highly recommend that you draw these two triangles for yourself and know how these rules work. There's going to be a practice quiz on Canvas that you can work through. And don't forget, you have unlimited attempts at those quizzes, but you're going to have to work through your practice quiz on Canvas and get at least an 80 before you can move on to the next section. So what we're going to do with these special right triangles is we're going to use what we know about the properties now to find some specific trig ratios. So I told you that the next unit is about the unit circle. The reason that we're doing this is the unit circle is going to help us identify the values of specific trig ratios for a lot of different angle measures. So what we're going to do is we're going to start with sine of 30, which remember in radians would be sine of pi over 6. So we've got sine of 30, cosine of 30. So we're going to start with these two. So sine of 30, 30 degrees, sine is opposite over hypotenuse. That is x over 2x. And if I notice here, I'm using variables because I know that this relationship holds true for all 30, 60, 90 triangles. And what that means is when I look at this ratio right here, x divided by x is 1. So sine of 30 is 1/2. Because I used variables here that represent any situation, that means that no matter the triangle, sine of 30 is always 1/2. Now let's do the same thing with cosine of 30. I see square root of 3x over 2x. So this is square root of 3 over 2. All right, so now I've got sine of 30 and cosine of 30. So no matter what, sine of 30 is always 1/2. Cosine of 30 is always square root of 3 over 2. Remember, 30 degrees, this would be the same as sine of pi over 6. And this would be cosine of pi over 6. All right, so now let's do sine of 60 and then cosine of 60 degrees. So before we do this, remember this would be the same as sine of sine, not sime. Sine of pi over 3. Because remember, pi is 180 degrees, so 60 is 1/3 of that, so it's sine of pi over 3. And then cosine of pi over 3. So instead of actually doing the ratios, again, I know it's not much work to do it, but we already know sine of 30 and cosine of 30. So sine of 30 must be the same as cosine of 60 because the sine of an angle is equal to the cosine of its complement. Remember, complementary angles add up to 90 degrees. So if this is sine of 30 degrees, cosine of 60 degrees, those add up to 90, which means that cosine of 60 must be 1/2. And I can do the same thing with sine of 60 being equal to cosine of 30. So that is square root of 3 over 2. All right, so these are 4 very important trig ratios. Sine of 30 is always 1/2. Cosine of 30 is always square root of 3 over 2. Sine of 60 degrees, square root of 3 over 2. Cosine of 60, 1/2. So we're going to use that when we get to the unit circle, which is next lesson. So then let's take a look at the 45, 45, 90 triangle. So with these, I want to find 2 ratios. I want to find sine of 45 degrees and cosine of 45 degrees. And remember, I'm going to start working in radians also. So I also want to make sure that I know what this is in radians. This is sine of pi over 4 and cosine of pi over 4. All right, so let's start with sine of 45 degrees. Remember, once we find this, it must be the same as cosine of 45 because these 2 angles are complementary. So sine of 45, opposite, x over hypotenuse, square root of 2x. This is x over square root of 2x. X divided by x is 1. So this is 1 over the square root of 2, which we've already rationalized once, and that gave us the square root of 2 over 2. And again, cosine of 45 must be the same because these 2 angles are complementary. So cosine of 45 degrees is also square root of 2 over 2. So we just learned 6 very important trig ratios that will always be true no matter the situation. Sine of pi over 4, sine of 45 is square root of 2 over 2. Cosine of pi over 4, cosine of 45 is square root of 2 over 2. And then we just talked about these 4 over here. So we got sine of pi over 6, cosine of pi over 6, sine of pi over 3, and cosine of pi over 3. So this is going to create the basis of what we call the unit circle, which we're going to be going through next class. So today's topics were about 30, 60, 90 triangles, 45, 45, 90 triangles, and special trig ratios. So in class, what we're going to do is we're going to take these special right triangles a little bit, not really a little bit further, but we're going to use the properties to help solve right triangles, meaning find all the sides. So if we have one side, we can find all the rest of them. So again, remember before class, make sure that you come with your notes, ready to ask any questions. And I thank you guys for watching today. And now we're going to stop cooking. So I hope you enjoyed, and I will see you in class. Have a good day.